Gas and liquid chromatography are versatile analytical techniques designed to separate, identify, and quantify components in a mixture. Chromatography relies on the interaction of analytes, the compounds being analyzed, with a stationary phase and a mobile phase. In gas chromatography, GC, the mobile phase is a carrier gas that transports vaporized analytes through a stationary phase within a column. In liquid chromatography, LC, a liquid mobile phase carries analytes through a stationary phase, which is usually a packed solid material. Chromatography works based on the principle of differential partitioning, where components of a mixture interact with the stationary phase to varying degrees, leading to separation as they travel through the system at different rates. For example, GC is used to separate and analyze components of gasoline, while LC identifies complex biomolecules like proteins in biological samples. An analogy for chromatography is separating puzzle pieces by color and size to reveal the complete picture of a complex mixture.
Gas and liquid chromatography are versatile analytical techniques designed to separate, identify, and quantify components in a mixture. Chromatography relies on the interaction of analytes, the compounds being analyzed, with a stationary phase and a mobile phase. In gas chromatography, GC, the mobile phase is a carrier gas that transports vaporized analytes through a stationary phase within a column. In liquid chromatography, LSC, a liquid mobile phase carries analytes through a stationary phase, which is usually a packed solid material. Chromatography works based on the principle of differential partitioning, where components of a mixture interact with the stationary phase to varying degrees, leading to separation as they travel through the system at different rates. For example, GC is used to separate and analyze components of gasoline, while LC identifies complex biomolecules like proteins in biological samples. An analogy for chromatography is separating puzzle pieces by color and size to reveal the complete picture of a complete picture of a complete picture of a complex mixture. Gas chromatography uses an inert carrier gas, such as helium or nitrogen, as the mobile phase to transport vaporized analytes through a stationary phase coated along the interior of a long, thin column. The stationary phase is often a liquid polymer or solid material that interacts selectively with the analytes based on their chemical properties. As the analytes travel through the column, components with lower boiling points or weaker interactions with the stationary phase exit, while those with higher boiling points or stronger interactions take longer. This results in the separation of the mixture. The eluted analytes are detected using techniques such as flame ionization detectors, FID, or mass spectrometry, GCMs. For example, GC separates components in essential oils, identifying their unique volatile compounds such as terpenes. GC can be likened to a marathon where lighter, faster runners finish first, while heavier, slower ones take longer to cross the finish line. Liquid chromatography uses a liquid solvent as the mobile phase to transport analytes through a column packed with solid stationary phase particles. The separation mechanism depends on the specific type of LLC being employed, such as reversed phase LC, where nonpolar stationary phases interact strongly with nonpolar analyte size, exclusion LLCA, which separates molecules based on size, and ion exchange LCI, which separates all cues based on charge interactions. High-performance liquid chromatography. EC uses high pressure to force the liquid through the column, resulting in faster and more efficient separation. For example, HAPC is used to determine the caffeine content in beverages like coffee and tea. LC is like a sieve sorting objects of different shapes and sizes as they pass through. The stationary phase in chromatography provides a surface for analytes to interact with and is key to achieving separation. In GC, it is typically a thin film of liquid polymer or a solid adsorbent coating the column interior. In LC, it consists of finely packed solid particles such as silica or chemically bonded phases, with specific properties tailored to interact with the analytes. The mobile phase is the medium that carries the analytes through the stationary phase. In GC, it is an inert gas, ensuring no reactive interference. In LC, it is a solvent or solvent mixture that can be adjusted to optimize the separation based on the analyte's polarity or other properties. For example, in reversed, phase H plus C, a non-polar stationary phase interacts strongly with hydrophobic compounds, allowing polar compounds to elute faster. The stationary phase can be likened to a host offering varying levels of hospitality to guests. Analytes, while the mobile phase ensures the guests move along. Gas chromatography is particularly effective for analyzing volatile and semi-volatile compounds. Its ability to separate complex mixtures makes it invaluable in environmental monitoring, petrochemical analysis, and forensic toxicology. GCMs, a combination of GC and mass spectrometry, allows for the precise identification and quantification of compounds based on their mass spectra. For example, GC is used in forensic labs to measure blood alcohol content, BAC. By analyzing ethanol levels in blood samples, GC can be seen as a magnifying glass that reveals the intricate details of gaseous mixtures. Liquid chromatography excels at separating non-volatile, polar, and thermally unstable compounds. It is a cornerstone technique in pharmaceutical quality control, food safety analysis, and biochemical research. LC can analyze large biomolecules such as proteins, peptides, and nucleotides, which cannot be vaporized for GC analysis. High-performance liquid chromatography, APLC, is used extensively for drug development, ensuring the purity and consistency of pharmaceutical formulations. For example, APLC is used to detect pesticide residues in fruits and vegetables to comply with food safety standards. LC is like a skilled detective uncovering hidden molecules in complex mixtures that would otherwise go unnoticed. Detectors are the key to identifying and quantifying separated analytes in chromatography. Flame ionization detectors, flame ionization detectors, are common in GC and detect hydrocarbons by ionizing them in a flame. Thermal conductivity detectors, TCD, measure changes in thermal conductivity for gas phase analytes. Ultraviolet, visible detectors, VVIs, are common in LC and measure the absorption of light by analytes, enabling quantitative analysis. Mass spectrometry, MISS, when coupled with GC or LC, provides detailed identification based on the mass-to-charge ratio. For example, GCMs is used in environmental studies to identify and measure trace levels of pollutants like benzene in air samples. Detectors are like translators, converting the language of molecules into interpretable data. Gas chromatography is highly effective for volatile compounds, offering fast analysis and high resolution, but is unsuitable for non-volatile or thermally unstable analytes. Liquid chromatography is versatile and capable of analyzing a wide range of compounds, but is slower and requires more complex sample preparation compared to GC. Choosing between GC and LC depends on the chemical nature of the analytical outcomes and the desired analytical outcomes. For example, GC is ideal for analyzing hydrocarbons in fuels, while LC is better suited for analyzing amino acids in biological samples. GC and LC can be seen as specialized tools, each designed for different tasks, one for volatile compounds and the other for complex, non-volatile mixtures. The future of chromatography focuses on increasing efficiency, sensitivity, and environmental sustainability. Ultra, high-performance liquid chromatography, ULTRA, improves separation speed and resolution. Advances in miniaturized and portable systems allow for field-based applications, such as on-site environmental testing. Green chromatography emphasizes reducing solvent use and waste, aligning with global sustainability goals. Integrating artificial intelligence enhances data interpretation, making chromatography faster and more accessible. For example, portable GC systems are used in space missions to analyze the chemical composition of planetary atmospheres. Future advancements in chromatography are like upgrading from a horse-drawn cart to a self-driving car. Faster, more efficient, and smarter.